Hey everybody, this next video lesson is going to talk about phase change and states of matter, and eventually get into the energy required to change the state of matter of a substance, and in this class specifically water. Have you ever stuck a thermometer into ice cold water and monitor the temperature change as it sits there and warms up into the atmosphere? Chances are you have not done this before. But if you take an ice water bath and stick a thermometer in, it's probably going to read about 0 degrees Celsius. Now maybe slightly above, but at or about 0 degrees Celsius. Now here's the thing about this ice water. This cup of water with ice in it could sit here all day and the ice would eventually melt. But as the ice is melting, the temperature remains 0 degrees Celsius for the entire process of the melting ice. And this is an observation that holds true every time it happens. A phase change is never associated with a temperature change. It could sit here and warm up in the atmosphere, melting the ice, but the temperature remains constant at or about 0 degrees Celsius. Now, if the beaker were all water, the heat added to the water would increase the temperature, but the fact is that there's ice being melted in this water, and so there's a phase change happening. So why doesn't the temperature change? When there is no phase change happening, an increase in heat goes to speeding up the particles. But during a phase change, any heat that's absorbed by the substance goes into breaking these intermolecular forces. These intermolecular forces are weak attractive forces that bind particles together, and if the temperature is cold enough, these particles solidify in the form of ice in water's case. And so if I'm trying to break those bonds, those weak attractive forces, I need to add energy, as we talked about in our chemical reaction video lesson from earlier this chapter. Any energy that goes into a substance goes into breaking its bonds if it's at the proper temperature to go through a phase change. So these two particles of water are cold enough to be ice, and I'm going to heat up the particles, and the particles will move faster until it gets to 0 degrees Celsius. At that point, any heat added goes to breaking these intermolecular forces, which allows them to turn into liquids. The same happens at 100 degrees Celsius when these liquid particles break their intermolecular forces that are still present and escape to vapor. So a phase change happens at the melting point and at the boiling point of a substance. You're looking at a cup of ice water that's being stirred, and I'm monitoring the temperature. As you can see in the upper right hand corner, I'm monitoring the temperature and graphing it. And as you can see, I'm adding heat, and you can see the little bits of ice inside the cup. Since there is ice, all that heat is going to break in those intermolecular forces. But see right here, now the ice is all melted and now the temperature can increase. We talked about how the temperature doesn't increase until all of the intermolecular forces were broken. Now I sped this up so that we can get to the boiling point much faster. But you'll see that the graph begins to once again level off as we approach the boiling point. Remember again, you are adding heat, and at this point the heat is going to increase in the temperature of the particles. But as soon as you begin boiling, the temperature is going to level off at 100 degrees, and once again that heat will then contribute to breaking of the intermolecular forces and not going to increasing the temperature of the liquid water. Let's take a look. You can see the bubbles forming in the beaker, and you can see on the graph that it stopped increasing and leveled off and now is going to run horizontally. Let's take a look at the calculations of a phase change. Now here's the thing, if I ask you to quantify the energy needed to melt ice, you only have one formula in your tool bag. It's mc delta T. But I told you that an energy change or a phase change doesn't correspond to a temperature change. In that case, delta T would be 0. And if delta T is 0, then Q is going to be 0 because anything times 0 gives you 0 joules of energy. So because the temperature change is 0, you can't use this formula when discussing the energy lost or gained from a phase change. So there must be another formula that we can use to calculate the heat lost or gained when a phase change happens, but we'll get to that here in a little bit. By now you should be pretty familiar with the three states of matter that water exists in normal atmospheric conditions. There are a couple of states of matter that exist at high temperatures and low temperatures, but these are the three that exist at normal temperatures on Earth. Now we use fancy words or fancy verbs used to describe the changes between these three states of matter. The first one is going from solid to liquid. So let's zoom in on that particular area. The word we use to describe the change between solid and liquid is fusion. You and I would probably call fusion melting, which is what a normal person would call it, but this is a chemistry class and chemists call this fusion. Now, the process of mixing from liquid to gas has a technical word as well, and we call that vaporization. To vaporize or make gas out of liquid. Now, there are words to describe the opposite effects as well. If we were to go down from gas to liquid, the opposite of vaporization is called condensation. And the opposite of fusion is called solidification. Now, the reason that we've established these words is because we're going to use them in the next part. The energy lost or gained by a phase change depends on two variables, and we're going to reference one of these two variables using these four words. That formula is Q equals delta H times moles, where Q once again is the energy lost or gained, but this time by a substance going through a phase change. It is important to note that this is in kilojoules of energy. This is different from the last formula because Q was in joules when it's equal to mc delta T, but here Q is in kilojoules. Now delta H represents something called the molar heat. The molar heat is a number that you're going to use, and you'll always be given this number. The number you use depends on if you're fusing, solidifying, condensing, or vaporizing. It's all dependent on what's happening in the problem. You're going to pick the molar heat value that matches what you're trying to do in the problem. And finally, moles is moles. It's the quantity of the substance. Usually, you'll be given grams of a substance, and you'll have to convert to moles using the molar mass. And in this class, the substance that we are going to focus specifically on is water. Now, these words could be applied to any substance, but we are only going to focus on water. And because of that, the molar mass is going to be one that you use a lot. And you're going to use it so often that you're going to remember that the molar mass of water is 18.02 grams. That's O plus H, or 16 plus 1.01 plus 1.01 equals 18.02. Now, before I show you a practice problem, I'm going to talk about these molar heat values. Now, these molar heat values are usually going to be things that are given to you, but you're going to use them so often that you'll probably memorize them eventually. So let's talk about the numbers associated with these different processes. The heat of fusion, or the heat necessary to melt ice, is always 6.01 kilojoules per mole. That's how much energy per mole is absorbed to melt ice. Now, you'd be correct in thinking that if it takes that much energy to melt ice, then there must be energy given off when liquid water freezes to form ice, or the opposite, solidification, and you'd be correct. That's kilojoules per mole released. Now, the energy absorbed by liquid water to vaporize is identified as 40.7 kilojoules per mole, and the energy released upon condensing is negative 40.7 kilojoules per mole. You will use one of these four every time you do problems involving phase change with water. So let's zoom out here and finally get to the formula and apply it to a problem. The formula, once again, is delta H times moles, and you're just going to use one of these delta H values, plug it in here, and multiply by the number of moles. Here's a practice problem. Practice problem. We've got 50 grams of water at 0 degrees and it freezes. And so I'm going to set up Q equals delta H times moles. Since I'm freezing, I use this molar heat that is for solidification, which is negative 6.01 kilojoules per mole. This is the amount of energy released per mole. Now I need to figure out how many moles 50 grams is. Well, 50 grams over 1, and this is of water, so 1 mole is 18.02 grams. When I divide these, the number of moles is 2.77 moles. So now what I do is I take that number of moles and I multiply it by the molar heat of solidification to calculate Q. And when I multiply these two together, I get negative 16.7 kilojoules of energy, which represents the energy released when something freezes, specifically 50 grams of water. Just a reminder, you will always be given this delta H value. You'll never have to memorize them. And the heat curve basically puts together a Q equals mc delta T calculation with a delta H times moles calculation into one large two-step or multiple step problem. First and foremost, let's talk about the heat curve. It is a graph of the temperature versus heat that is applied to a sample of substance. Here is the heat curve, at least the beginnings of it. We've got temperature on the vertical axis, as you can see, in degrees Celsius, and we've got heat along the bottom or along the horizontal axis. Heat curves can be drawn for all different types of substances, but in this class we're going to focus on one substance that's very common, water. Now when it comes to water, there are two important temperatures, and the temperatures I'm talking about are the temperatures at which water changed state of matter. Those temperatures are 0 degrees and 100 degrees Celsius. Now let's imagine you have a very small piece of ice, maybe an ice cube, and you've pulled it out of a freezer, and that freezer started at like negative 20 degrees Celsius. Let's mark that point on the vertical axis. So you begin applying heat to that piece of ice, and its temperature of the ice increases and increases and increases until it reaches 0 degrees Celsius, at which point that ice now begins the process of changing state of matter. We talked about in a previous video lesson that in a change in state of matter, you add heat to the substance, but its temperature does not increase. In fact, the temperature won't increase until all of that substance is changed from solid to liquid in this case. So we continue to add heat to this sample of ice, and you'll notice that the temperature levels off for a period of time. That leveling off represents the phase change between solid and liquid. The technical term for this process is fusion, or melting. Once that sample of ice is all melted and is turned to liquid, adding heat begins to increase its temperature once again, and will continue to increase at a linear rate until once again it reaches a temperature at which it begins changing state of matter. That temperature is 100 degrees Celsius. At that time, the graph, although still increasing in heat, does not increase in temperature and levels off again for a period of time. This point of the graph represents vaporization. If we were able to collect all of that liquid water turning to steam and collect it in like a tank or some sort, and then we can take all of that steam and continue to increase its temperature on further and further and further and further up until technically an infinite temperature. But we'll stop here for now. This is the heat curve for water, starting at negative 20, going up to 0 and melting, and then taking it from liquid water from 0 to 100, vaporizing, and then taking the water vapor from 100 up until a temperature until you want to stop. Now, one thing a heat curve is useful for is that if at any point on this curve I ask you to pick a temperature, you could tell me the state of matter. So for example, if I say negative 10 degrees, well, it's 0 is here, so negative 10 must be somewhere around here. And this portion of the graph below 0 represents water as a solid. If I ask you to pick a part of the graph that's between 0 and 100, maybe 50 degrees, you're going to fall on this particular part of the graph between 0 and 100. This area is the area in which water exists as liquid. And finally, if I tell you the sample of water is above 100 degrees, maybe it's 110 degrees, and so you're looking at someplace up here above 100, because this line always lies on 100, so you're above the line, then you're talking about this section of the curve, which is known as gas or water vapor. We'll label it gas. If you were asked to describe the state of matter at some point along the flat portion of the graph, it would be really hard to describe what's happening there, because the state of matter is kind of a mixture between the two states of matter on either side of the line. I'm pointing to the one up here at 100 degrees. At any point along this line, you are some part liquid, some part gas. And so it would be impossible for me to ask you what state of matter exists here. But if I said it's below 100 but above 0, you'd say it's liquid. Same is true with this one down below. This is the line that represents the transition between solid and liquid. If I ask you what part or what state of matter does this line represent, it's both solid and liquid. In fact, if you zoom in at a particular part of this graph right now, this intersection point between where the line comes up and levels off, it represents solid at exactly 0 degrees. Because the moment a solid turns to 0 degrees, it begins melting, and the curve no longer goes up, but lays out flat in a plateau sort of way. Similar to this other side of the flat portion, where the intersection stops going horizontal and begins increasing in a positive slope, that is a very important part of this graph as well, because that area represents liquid water at 0 degrees. So it's important to note that anywhere between the solid at 0 and the liquid at 0 could be a mixture of both solid and liquid. But this point, this exact point right here, which I will identify with a dot, a black dot, is solid at 0 degrees. And this point right here represents liquid at 0 degrees. Now let's scroll up to the other phase change that water goes through, the transition between liquid and gas. And this point right here, where it stops going up and begins going horizontal, is liquid at 100 degrees. And this part of the curve right here, where it stops going horizontal and begins increasing again, shows me the part where it is gas at exactly 100 degrees. And again, these two are very important points of the graph, so it's important to know where they are and what they represent. Whenever the graph changes direction, that's an important part of the graph, so know those points. So far we only talked about what happens when you heat up water, going from left to right and vertically on the heat curve. But you can use the heat curve also in a process of cooling down, where you have something that's hot and you cool down and condense, cool, and even solidify. So I'd like to take some time to add in parts of the graph that represent the opposite of fusion and the opposite of vaporization, which are solidification and condensation. Because this heat curve could act both endothermically if you're moving up and to the right, or exothermically if you're moving down or to the left. Finally, the most important thing that I'm going to ask you to do as it pertains to the heat curve is to be able to quantify or calculate the amount of heat that water absorbs or releases when heat is added to a sample of water. Now that water could start out as ice, or it could be liquid, or it could be gas. The two tools that we learned about in this chapter that are used to quantify heat, or Q, are the two that have Q equal to something. The first one is Q equals delta H times moles. And again, we use this formula whenever we're calculating the heat lost or gain from a phase change or a change in state of matter. The other one is Q equals mc delta T. And we use this formula whenever we're trying to calculate the heat lost or gain when a substance just simply absorbs heat and changes temperature. Now the key difference here is that one of these can be used to measure a change in temperature and one of them cannot. The phase change has no change in temperature, but the mc delta T indeed has a change in temperature. And the heat curve can be used to solve problems, word problems, that ask you to quantify the heat lost or gained in a multi-step problem. Examples are what I'm going to show you on the next slide. But let's talk about the parts of the graph that use these two different equations to solve for Q. Now, anytime you're dealing with a horizontal part of the graph at the solidification slash fusion temperature or the vaporization slash condensation temperature, you're going to use delta H times moles to calculate or quantify the energy lost or gained along the flat portion of the graph, the horizontal flat portion. And that means that the other three parts of the graph, because there's really 5 parts of the graph, there are 3 states of matter, solid, liquid, gas, and then there are 2 phase changes, so you can think of it as 5 separate parts, 1, 2, 3, 4, and 5. Now the other 3 parts use Q equals mc delta T to calculate or quantify the amount of energy lost or gained during a temperature change. And I'll refer to the parts of the graph as either phase changes or temperature changes. Phase changes are horizontal and temperature changes go up and down. Here's an example problem that would utilize the heat curve to help you organize your thoughts and organize the steps in which this problem is going to be executed. Because it's not just a single step, in fact, it's 2 steps. We'll talk about it as we draw or sketch a quick heat curve. So I'm going to sketch the vertical and horizontal axes. I'm going to do 5 lines alternating vertically with 2 horizontal. Now what I like to do is I like to mark the starting temperature and the ending temperature and state of matter. Because in each problem there's going to be a starting temperature and state of matter and an ending temperature and state of matter. For example, in this problem, we begin with 70 degrees as liquid water. So I'll draw a line right here that's somewhere between the 0 and 100 along the liquid section of this graph. Remember, solid is this area below 0, liquid is between 0 and 100, and finally gas or vapor is above 100. So the start temp and state is marked on the sketch T-curve. Now the final ending temperature is 100 degrees, and the final state of matter is vapor. It becomes steam. Now remember, we talked about how along this line, which represents 100 degrees Celsius, this side represents liquid at 100, where this corner represents gas at 100. And gas at 100 is where I'm going to end. What that means is if I zoom in on this problem, I'm going to execute this problem in 2 steps. First, I'm going to calculate using mc delta T the amount of energy it takes to warm up the water to 100 degrees. I'm going to take it from 70 to 100. Next, I'm going to take the water at 100, and then I'm going to vaporize or boil. And for this part of the problem, I'm going to use delta H times moles. And when those 2 problems are done, I'm then going to take each one and I'm going to take the sum or add them together to get my final answer, which I will then box. So let's zoom back out and begin working this problem. Step 1 is to heat up the water. Now the mass of the water is 15 grams and the specific heat of water is 4.18 joule per gram degrees Celsius. Now these specific heat values and delta H values, which you will need to calculate vaporization, will always be given to you. These are things that will always be given to you on a data table that you will use. And so don't have to worry about memorizing them. But you do have to know which formula to use in which situation. So 15 grams times 4.18 times the temperature change. Now it goes to 100, which is my final, minus 70. In other words, it's a 30-degree temperature change. Now I hit equals here and figure out how many joules of energy are going to be absorbed, because grams cancel, degrees Celsius cancel, these are degrees Celsius, and the only thing left is joules. So this first step represents the energy that is added to the water to heat it up. Now that it's boiling, I need to calculate the energy that it takes to vaporize all 15 grams of water. And in order to do that again, I'm going to use delta H times moles. So that being said, I'm first going to figure out what delta H for vaporization is. Again, I'm going to pull that off a table. That table tells me that it's 40.7 kilojoules per mole of energy, and I'm going to multiply that by the number of moles. But I don't have number of moles, I have number of grams. This is a simple calculation. If I know the grams, I can easily calculate the moles if I know the molar mass of a substance. And the molar mass of water is always 18.02. So if I multiply 15 divided by 18.02, I get 0.832 moles. And that 0.832 moles goes right here, and I simply multiply these 2 numbers together to get the amount of energy gained for vaporizing water. The answer is 33.9 kilojoules. Now the last thing I need to do is add these together, but I can't add them together currently because the numbers are not going to add together nicely. One's in joules and the other's in kilojoules. And what I like to do is convert all of my joules to kilojoules by moving the decimal over 3 to the left. So it becomes 1.881 kilojoules. Now I can add 1.881 kilojoules to 33.9 kilojoules, and my final answer is 35.8 kilojoules of energy. That's the energy from increasing the temperature from 70 to 100 added to the energy needed to vaporize the water. This was a 2-step process. Now before I finish off this video lesson, I'm going to talk about the 4 common mistakes that I see when students execute these problems, and these come up time and time again. The first thing I notice is that students use the wrong C value. And that means that when they really want to use the one for water, they use the one for steam, or when they want to use the one for ice, they use the one for water. Here's a little bit of some information to help you remember which C value to use. If your temperature change is happening below 0 degrees Celsius, then you want to use the ice specific heat. If your temperature change is happening between 0 degrees Celsius and 100 degrees Celsius, you want to use the water one. And if your temperature change is happening above 100 degrees Celsius, then you want to use the one for gas or for steam. Similar to the mistake from up above, the second one is that students use the wrong delta H value. Very rarely will I actually use these vocabulary terms in the problem, but rather I'm going to write a narrative describing the change that the state of matter goes through. And so you need to look at what state of matter you start in and what state of matter you're changing to in order to figure out which delta H value you're going to use. If you're going to go from solid to liquid, you're going to use the heat of fusion. If you're going to go from liquid back to solid, you're going to use the solidification. Vaporization is going from liquid to gas, and finally condense is going from gas to liquid. So pay close attention to those clues to help you determine which H value to use. Every once in a while, you'll see students not convert their numbers to be a consistent unit. Now, I convert to kilojoules, but that's just because I like kilojoules more so than joules. But you can convert all your numbers to joules. Either way, as long as you convert all your numbers to the same unit before you add them up, you will get the correct answer. But if you don't, you're going to get a number that's way off. So make sure that you convert all of your numbers to all joules or all kilojoules before you add up your final answer. And finally, the last thing that I see commonly is that students forget to split their delta T's apart into two smaller delta T's if the full delta T is interrupted by a phase change, similar to the second practice problem I showed you just on the last slide. The full change in temperature was 75 degrees drop, but the first 70 was as water, so my delta T for the first step should be 70, and the last 5 degrees was for ice, so my last delta T should be just 5 degrees. Students often use the full delta T while calculating, and they get the wrong answer. Well, hopefully you have a little bit more clear picture on what heat curves are and how to calculate them, and specifically how to use the heat curve to help answer some practice problems that include multiple steps. That takes care of this video lesson. Thanks for listening.